Hello AP Physics students, it's Dr. Brenzi here, and this is an example problem from lesson 7.9. This lesson is about angular momentum and its conservation in collisions. So a problem that you might come across in lesson 7.9 and on the AP exam, especially the free response section of the exam, is an angular momentum collision. So we have a bar right here, and it has a mass, it says, of 3 kilograms and a length of 1.2 meters. And they have a 1 kilogram ball colliding, striking the end of this bar, and its initial velocity is 10 meters per second. And then after the collision, the ball travels at an angle, theta, relative to its initial velocity. And we're being asked, what is that velocity v and what is that angle theta? Now, one other thing that I didn't have enough room to type in here is what happens to the bar after the collision. After the collision, the bar goes from this vertical position here up to a horizontal position here, and this is where it stops. I wasn't able to include that important detail in the problem, but that's going to actually help us figure out what its kinetic energy was immediately after the collision. That's also another reason why they made this an AP style problem here, because they love adding complexity like that, where you have to use multiple concepts. Okay, well, let's get started here. First of all, this is a problem that will involve angular momentum being conserved because there are no external torques acting on the system. The only torque that occurs is when this ball strikes the rod, and both of those are part of the system, so that's not an external torque. Kinetic energy is also conserved through the fact that they said that it's an elastic collision. But one of the things that's not conserved in this problem is linear momentum. Now, the reason that linear momentum is not conserved in this problem is that this ball, after the collision, has a vertical component of its velocity, which means that before the collision, something had to have a vertical component of its velocity over here in order for linear momentum to be conserved. But that's not the case here. We only have something traveling horizontally, which means that it's impossible for momentum to be conserved in this situation, at least linear momentum, excuse me. Well, if linear momentum is not conserved, and this is kind of a side note here, then we must have had a net external force acting on this system. And it turns out that net external force is actually coming from where the rod is fixed to whatever, this is. I don't know if this might be something hanging down from the ceiling or something like that. But this thing, it actually produced an external force on the bar, because normally the bar, if the ball, is experiencing a force in that direction from the bar, then the bar had to experience an equal and opposite force in that direction, which meant that this pivot point would have started moving in that direction, but it doesn't. It remains stationary because there's a force coming externally from the support for the bar. So that's why linear momentum in this situation is not conserved. But if we didn't have this stationary pivot point, then we could say that linear momentum is conserved, but then this would become a very much more complicated problem. Well, let's go back to the problem that we're dealing with here. So let's start off with angular momentum conservation. So let's figure out what the angular momentum was before the collision and compare that to the angular momentum after the collision. Now, the ball is not attached to the pivot point in any way, shape, or form. So it wouldn't seem from first approach that this would have some sort of angular momentum. But what you can say is that immediately before the collision, we can pretend as though it does have angular momentum. And the formula for that angular momentum is usually what you see in textbooks. Let me talk about that in a moment here. Is mass times velocity times either r or d, where d is the distance from the pivot point to the ball or the object. So a single point mass will have mass times velocity, and very often you'll see this as r, but I decided to make it d. What you don't often see is actually this term sine theta, which doesn't have to be there as long as the angle between the radius, which would be, oh darn it, sorry about that. I pressed the wrong button at the wrong time. This is like the second time I've recorded this, and I had the same problem. Let me try to avoid that. Okay, so this would be the radius vector, r. Oops, r. And this is the velocity vector, v. And in most physics textbooks, at least introductory textbooks, they always assume that this angle is 90 degrees, but it doesn't necessarily need to be so. As you can tell after the collision, that's definitely not 90 degrees. So we definitely need that sine theta component in our formula. So I'm going to call the ball M1, and I'm going to call the bar M2. Let me erase those comments that I just made there about R and V. Don't need those anymore now that you understand where that sine theta term comes from. Okay, so the angular momentum of the ball just before the collision is mass times velocity times its distance from the center times sine theta. And in this case, theta is 90 degrees. And so we can just plug in the information we were given in the problem. And we get an angular momentum of 12 kilograms meters squared per second. The bar is stationary, so it has no angular momentum, so we can write L2 is equal to 0. So the total angular momentum before the collision was just the angular momentum of the ball, which is 12 kilogram meters squared per second. Okay, now let's turn our attention to what happened after the collision. So now let's calculate the angular momentum of the ball immediately after the collision happened. We're going to have the same formula, m1 v1 d sine theta. But now theta is no longer 90 degrees, so we can't plug anything in for that. All I can plug in for is mass and its distance from the pivot. So I'm going to actually get an expression for L1, the angular momentum of the ball. And the angular momentum of the rod is going to be its moment of inertia times its angular speed. The moment of inertia of a rod that's rotating around one of its ends is going to be 1/3 ml squared. And then we don't know what its angular speed is, so we have to leave that as omega. So just by using angular momentum, if I had been given this omega, then I could solve this problem, but I'm not. Instead, what I was given is the fact that this bar swings up from its vertical position up to a horizontal position 90 degrees and then comes to a stop. So I have to use that information in conservation of energy to figure out what omega is. So I have to take a little sidetrack here. All right, so let's go down that road. I'm going to rewrite the angular momentum equation for that bar, what we had so far. And you'll see in a moment why I wrote it down here in this strange place. And then, okay, so here's the bar. And its pivot is up at the top, but its center of mass is in the middle here. And the center of mass will swing from this position up to that position. The reason I say that is because we have to use the center of mass when we are calculating the object's potential energy when it gets to the top. Its kinetic energy, we know, will be 1/2 times I times omega squared, so that's how much energy the bar will have when it's vertical. But when it goes horizontal, its gravitational potential energy is m times g times the height of the center of mass. Okay, it's not the height of the rod, it's the height that the center of mass increases. That happens to be just half of the length of the rod. So be careful when you're using conservation of energy that involves rigid bodies. You're not going to look at the very bottom of the object. You have to look at where the center of mass started and how much higher it ended up. All right, so let's set up our conservation of energy equation here so that we can figure out what this omega is, the angular speed. Okay, when the bar is vertical, it has kinetic energy 1/2 I omega squared. Whoa, I'm going a little fast here. Whoops, sorry about that. Let me back that up. I forgot to put some pauses in there. Okay, so that's the kinetic energy the rod will have when it's in the vertical position, just after it was struck by the ball. And then let's plug in its rotational inertia. There we go. And that's as far as we can get in the vertical right now. And then in the horizontal position, when it gets to its highest point, as I said, the height of the center of mass goes up is just the length of the bar divided by 2. So be careful about that. Okay, conservation of energy says that we can set these two things equal to one another. So let's do that. There we go. And now we have an equation that we can solve. And all sorts of terms will start dropping out and dividing out, and multiplying out. Let's start off with these 1/2s on both sides of the equation. And then also one of these L's on the right-hand side will multiply out with an L on the opposite side, or divide out, excuse me. And then I think we have some M2s that will divide out. And when you straighten out all this mess, you'll have omega squared is equal to 3. That came from right here, this 1/3, G over L. And that L came from right here. So I had to divide both sides by L over 3. Take square root of that. And now we have an expression for the angular speed of this bar after the collision. I could put some numbers in there. I probably should have, but I didn't. I did it symbolically instead, because sometimes I love doing things the hard way. So let's go ahead and plug that into our angular momentum equation. And whoops, hold up, let me back up there. Let's see, it looks like my L disappeared there. Oh, actually, I see what happened. I was moving some things when I was editing this, and that needs to go right there. There we go, that's better. Okay, that's where the L should be. And need to simplify this over here. So when we do that, and now I finally plugged some numbers in. And once I evaluate this, I am going to get a number 7.13 kilogram meter squared per second. Okay. All right, so let's return our thoughts to the conservation of angular momentum that we had. So before the collision, we had 12 kilogram meter squared per second for the total angular momentum. Now after the collision, we have the angular momentum of the ball. We came up with that in the first slide before, and now we have the angular momentum of the bar as well after the collision. So now I have an expression for the total angular momentum after the collision. And now that, well, since angular momentum is conserved, I can set these equal to one another. And now I can solve for v times sine theta. And when I do that, I get v sine theta equals 4.06 meters per second. Now, if you think about that, what that is that is the horizontal component of the velocity of the ball after the collision. So if I had been given a problem where instead of the ball going down and to the right at some angle theta, if I had been told that the ball had traveled to the right horizontally, then I would only need to use conservation of angular momentum to figure this problem out. Problem is, that's not what they gave me. They asked me to figure out what the velocity of the ball is, and they asked me to figure out the angle. That's why I need to bring conservation of energy into the problem. So let's figure out what the magnitude of this vector is and figure out what the angle is. So I have one component of it, but I don't have both, which means I have to use conservation of energy. All right, so the collision is elastic, they tell us, so we can use conservation of kinetic energy in the collision. So let's figure out what the kinetic energy was before. That's 1/2 m1 v squared. And v was the velocity I had before the collision. So that ball, turns out, had a total kinetic energy of 50 joules before the collision. After the collision, we have the kinetic energy of the ball again. We don't know what its velocity is, but we can say that its kinetic energy is 0.5 times v squared because the mass of the ball was 1 kilogram. And the kinetic energy of the bar, I could initially say it's 1/2 I times omega squared, but why go and plug in that complicated moment of inertia and that expression for angular speed when I know that all of that energy became gravitational potential energy when the bar swung up to its maximum height? So let's just use m2 times g times how far the center of mass rose. Okay, when I do that, I get 3 times 9.8 times 1.2 over 2. And so that is a total kinetic energy of 17.6 joules. All right, so I set the total kinetic energy before equal to the total kinetic energy afterward. Now I have an equation. I can solve for v. So let's do it. Let's solve for v. And it turns out that v squared is 64.8. So v is 8.0 meters per second. All right, so just by using conservation of energy and the fact that this collision was elastic, I could figure out how much velocity the ball had to have after the collision. I still don't know what theta is yet, but I remember that from conservation of angular momentum, we got this result. So now I can plug in what v is, and I can find theta, and theta is 30.5 degrees. Okay, so that was a long problem. I know that this video is almost 20 minutes long, but just realize that, hey, sometimes the AP is going to throw a problem with that, or like this at you. Sometimes you just have to do more complicated stuff. They would probably do it in like multiple parts of questions. So, you know, this might like be part D or part E or something like that. So this is like the type of question that, you know, you'd get if you wanted to score a 4 or 5 on the exam. If you wanted to score a 3, then you probably should definitely be able to get this result from just using conservation of angular momentum. And that's what we did before we had to bring kinetic energy into the problem. Okay, team, so I left you a couple of practice problems that are not quite this complicated, so because I want you to kind of get used to just using angular momentum. So you're going to have a problem that would have you just figure out a horizontal velocity after the collision. Go ahead and practice that, and I will also post solutions to those practice problems so that you can go into the summative ready to rock it. Okay, team, I will see you on Tuesday, and I hope you have a good weekend. Bye.